Animate and Inanimate by William James Sidis. Chapter 13. The Nebular Hypothesis. So far, we have considered only a single cross-section in time of the universe in our astronomical considerations. That is, we have only considered the appearance of the universe at a given moment of time, and thus come to the conclusion that, at a given moment, the universe is built of positive and negative sections with a tolerably well-defined shape, as a consequence of our theory of the reversibility of the universe. But we have not yet considered the changes in the universe or in its constituent parts, the stars, that are brought about by time, what the universe was in the past, what it will be in the future, in short, the course of events that generates in individual stellar systems, or in the universe, its past, present, and future conditions. This branch of astronomy is known as Cosmogony. Let us, then, examine the recent theories on the matter of cosmogony. The first theory which had a scientific basis was the so-called nebular hypothesis. This hypothesis is interesting partly from the fact that it originated in the minds of three men independently at about the same time, these three men having arrived at it from three different points of view, and being in three different countries, while each was among the most prominent men in his own specialty. One of those three men was Immanuel Kant, the famous philosopher, who originated this hypothesis as an incidental speculative conclusion from his own philosophy. Another was the well-known mathematician Laplace, who arrived at the hypothesis from considerations of his studies of celestial mechanics, while the third originator of this hypothesis was Sir William Herschel, who is well known as an astronomical observer, and who arrived at the nebular hypothesis as an explanation of many phenomena he observed among the stars. According to this theory, which was quite generally accepted almost throughout the 19th century, the universe was once what the originators of the hypothesis have been pleased to call, probably after the Greek mythology, a chaos, which seems to mean undifferentiated matter uniformly distributed throughout infinite space. Centers of attraction were formed where, in any spot, the matter was slightly denser than in its vicinity, and surrounding matter was drawn into these centers. Thus were formed whirlpools, which set up a great rotation at each center, increasing with the increasing condensation at the centers. It was further assumed that the original chaos was at an intense heat, so that, at the centers of attraction, great, hot, rotating bodies were formed. The rotation became faster and faster as the matter was drawn in toward the center, the centrifugal force finally becoming so great that the rings of matter were thrown off. In each ring a center of attraction was formed, and the process was repeated. From the primary whirlpools there thus came the stars, from the centers of attraction resulting from the rings, came the planets, and these planets themselves threw off rings which finally became satellites. Since larger bodies cool off slower than smaller bodies, the stars and the largest planets remained hot, the smaller planets and the satellites cooled off to a solid condition. This theory was accepted generally throughout the 19th century, with occasionally some minor modifications. For instance, the assumption that the original chaos or universal nebula was in a state of intense heat had since been dropped, because the energy of matter coming in from a distance under the influence of gravitation would be sufficient to explain that heat would arise in immense amounts. When potential gravitational energy at a high level is reduced to a smaller amount at a proportionately lower level, the difference is converted to heat without loss under the second law of thermodynamics. This theory was corroborated by the supposed fact that the planets and stars in the various stages were visible to astronomers, such as hot planets, the major planets, such as Jupiter and Saturn, and even the ring around Saturn, stars in the various stages from extremely heated stars to almost dark stars, Algol's companion star being an example of a completely dark star, while the very first stage of star formation would be indicated in the many nebulas that are visible in all parts of the sky. One stage, of course, that was not exemplified in observation, was the chaos, or universal nebula, from which all stars supposedly originated. Further, in the explanation of how this chaos gave rise to stars, it is supposed that centers of attraction arose at the places of maximum density. But, since in the original chaos the density was assumed to be uniform throughout, the question naturally arises as to what miracle could have given the start by condensing some spots and rarefying others. In fact, this theory leads us back more obviously to some creative miracle than even the second law of thermodynamics. In the last half of the 19th century, further facts about the stars and about the solar system in particular began to be discovered, which made the original nebular hypothesis very improbable indeed, and which necessitated the formation of a new cosmogonic hypothesis. This gradually took shape in the form of what is now known as the planetesimal hypothesis, which, though partly based on the old nebular hypothesis, has altered the main ideas. This planetesimal hypothesis originated from the theory of tidal friction, as developed by George Darwin. According to this theory, when two dark stars, of which the universe is supposed to be full, come close together, being led to pass close to each other by their respective proper motions, the extreme proximity results in the two dark stars mutually raising immense tides on one another, the tidal friction being so great as to heat both stars to an immense heat, and at the same time to produce in each star a rotation in the plane of the relative velocity of the stars. Incidentally, the mutual attraction of the two stars would probably make a great change in the proper motions of both. The tidal force acting on each star would furthermore be strong enough to overcome the cohesion of the parts of the star, and thus tear almost all the exterior parts of the star away from the star into the surrounding space, forming a spiral nebula. This nebula, as thus formed, will contain many condensations of larger or smaller size. These, on cooling, absorb surrounding portions of the nebula, and become planets, satellites, asteroids, and meteorites. All these will tend to revolve around their sun in the same direction as their sun itself rotates, as well as to rotate on their own axes in the same direction. The planetesimal hypothesis thus tends to assume that the universe always was somewhat as it is now, but that stars come and go in generations, as it were. There are thus supposed to be at present stars of all sorts of ages, stars of the older generation, and young, warm stars of the newer generation. The very youngest stars are surrounded with nebulas, which are, indeed, usually found to take the form of spiral nebulas. The life of a star is somewhat as follows: after the process that has just been described, then first the planets and then the star itself cools off, possibly becoming dark, till proximity with another star comes about again, when the systems are once more heated up and proximity of the two stars generates in both a new planetary system. From the proximity of two stars there issues two new stars. And so the process keeps on from one star generation to the next. This planetesimal hypothesis is undoubtedly a plausible one, though, like every other theory, there are plenty of observed phenomena that it either does not explain or explains only imperfectly. No doubt, if two dark stars come into such proximity, that proximity will generate new stars with a planetary system to each, as that hypothesis assumes. And it is also true that almost all stages of growth of a star under the planetesimal hypothesis are actually observed in the sky, but, as in the case of the nebular hypothesis, the initial process is a missing link. The main common ground of these two hypotheses is, that there was a nebula which condensed into a stellar system, the stars, planets, etc., of the stellar system becoming constantly cooler as they radiate their heat into outside space. So much can almost be observed directly, for all these stages, from the nebula on, are exemplified in the sky. The ring stage as supposed in the original nebular hypothesis has, however, never been observed in any star, and the only possible example of that is Saturn's rings, which, however, is a spurious example, since spectroscopic observations show that the rings around Saturn are not true rings, but simply collections of small satellites at approximately the same distance from the planet, and which, from this distance, look like rings. However, practically all stages of the planetesimal hypothesis can be seen exemplified in the sky. The planetesimal hypothesis does not deny that sometimes a new body can arise by rotation, but, even in such a case, there is no ring process. In the case of the Earth, for instance, it is supposed that the Earth was rotating with extreme rapidity, the centrifugal force finally elongating it into a sort of pear shape, the elongation continuing until the centrifugal force at the end of the pear exceeds the gravitational attraction. Then the part of the Earth at the smaller end of the pear separated and became the Moon. Tidal friction afterwards slowed the rotation of both parts and the reaction moved the Moon away to its present distance from the Earth. The same origin may be supposed for many multiple stars. In fact, the various stages of this process can actually be seen among the stars, for there are variable stars whose variation in brightness could only be explained by this pear shape, and again there are those whose variation indicates that they are very close binary, physically double, stars, and again we have the visible binaries. It may be interesting to note that this process of origin of new bodies by rotation has a remarkable resemblance to the processes of cellular reproduction, only in the latter case surface tension and not centrifugal force produces the constriction and division. As we have stated before, one strong test of these hypotheses is the observation in the sky of stars in various grades of formation from the nebula to the dark star. The dark star itself is of course invisible, but all grades up to that can be observed, and, in fact, all grades of star development assumed by the planetesimal hypothesis, as far back as the spiral nebula stage, are actually observed in the sky. However, the crux of differentiation between the hypotheses is, what was the prenebular stage, what brought about these nebulas? The observational method of answering this would be, do we see in the sky any phenomena that would be likely to lead up to the formation of a nebula? The only such phenomena that can be observed are the so-called temporary stars, or novae. These are stars that suddenly flare up, last a few months, and then gradually fade out. Before the flare-up, nothing whatever is visible in the place where afterwards the temporary star appears. After the star fades out, it has simply radiated a great proportion of its newly acquired light and settles down to the usual brightness of the stars in its vicinity. However, it is a general rule that most temporary stars, if not all, are surrounded by a nebula. We may suppose that the explanation of the nebular condition as generally observed, most nebulas having one or more stars or star-like condensations in the center, could be found in the flare-up of the temporary star. This explanation would be very satisfactory if we only knew just what happens when a temporary star suddenly appears. It would seem that, by observation, the history of a stellar system cannot be traced back farther than the appearance of a temporary star, so that, if we wish to trace back the development of such a system, it would be important to find out just what makes a temporary star flare up. It seems to be the general consensus of opinion among astronomers that there is nothing in the appearance of a temporary star to make it even remotely possible to assume that they are due to collisions of bodies. A common theory is, that the flare-up is due to explosions of hydrogen. This may sound reasonable, until we notice that hydrogen is not an explosive substance unless in contact with a sufficiently large amount of some such substance as oxygen. We would thus have to suppose a body consisting of hydrogen meeting an oxygen shoal and then exploding. A temporary star, however, consists mostly of hydrogen, and hardly contains enough oxygen to make all that hydrogen explode. Furthermore, at such a heat as that of ordinary stars, still more so at that of temporary stars, water, which is the product of an oxyhydrogen explosion, could not exist, and its decomposition under the influence of the explosive heat would absorb just as much heat as the explosion produced, thus leaving our temporary star without any heat or light at all. Under the planetesimal hypothesis, it has been suggested that a temporary star actually consists of two stars approaching in proximity to each other and drawing out of one another heat and a nebula. This sounds very plausible, but is a bit difficult to support. Besides, it is difficult to see why most of these phenomena should occur in the Milky Way, that is, near the edge of the Herschel drum. In fact, it is not easy to understand exactly what does happen when a temporary star appears. We may possibly, however, benefit by the more detailed observations taken of Nova Persei 1902, a temporary star which appeared in August 1902, and in connections with which many strange phenomena were observed. This star was first discovered by a man who, though not a regular astronomer, was a habitual stargazer. One evening in August, 1902, he noticed in the constellation of Perseus a new second-magnitude star that he had never seen before. This discovery being made public, it turned out that, on the previous night, a photographic plate of that part of the sky had been taken at the observatory, showing stars down to the 12th magnitude, and yet the spot where this new bright star appeared was vacant on those plates. Evidently, within 24 hours, the star had flashed up to the second magnitude from a magnitude certainly less than the 12th, if indeed it gave any light at all, that is to say, it flared up suddenly at least 10,000 times its original brightness, if, indeed, it gave any light at all before the flare-up. One characteristic of this flare-up, then, was its suddenness. The time the star took to flare up in this manner is not known, but it certainly was only a matter of hours. But a far more interesting aspect of the affair appeared later. The star, indeed, appeared a bit hazy, but soon it was seen surrounded by a nebula, which kept on increasing in size. The nebula was approximately circular in shape, the radius of the circle increasing by about 5 seconds of arcade each month, which would make in a year about 1 minute of arcade. Since the star showed no parallax, so that its actual distance was too great to be measured, that meant that its distance was more than merely hundreds of light years, but rather ran into the thousands. The rate at which this nebula in motion was spreading, being about a minute of arc in a year, must be, in a year, about 1/3400 of the distance of the star, a minute of arc being about that fraction of the radius of the circle. This meant, if the distance of the star was to be measured in thousands of light years, that the rate of spread of the nebula was at least one-third the velocity of light, if not more. The most probable hypothesis was, that the rate was exactly the velocity of light, making the distance of the star about 3,400 light years. Now, since we could hardly suppose that any explosion, however violent it may be, or especially any result of tidal disruption, would produce matter which would actually move in all directions with a velocity so great as that of light, the observers were led to the hypothesis that the nebula was actually there before the star flared up, and that the apparent spread of the nebula was an illusion due to the actual spread of light through the nebula, first in the central parts, then gradually toward the edges. In other words, the conclusion was arrived at that the star was in a nebulous condition long before it began to give out light. This is hardly in accord with either the nebular or planetesimal hypothesis, for, on the first, light would not be a sudden development, and, on the second, both light and nebula originate at the same time, the light reaching outside points long before the nebula. In fact, we may say as a matter of observation that only the stars which appear to be of the older generation are surrounded by nebulas. We should therefore conclude that a nebula is some supervaporous phenomenon which is only possible as the result of such extreme heat that the vibration of many particles gets them almost altogether away from the influence of gravitation. Thus, the conclusion that the nebula existed previously to the flare-up can only mean that the star was, before it suddenly flared up, in as hot a condition as afterwards. This can only mean that the flare-up could not have been due to the sudden accession of heat that might be supposed under the influence of either tidal friction or of a collision or explosion. The heat was there before, but somehow or other it did not transmit itself into outside space. But, since such transmission of heat into outside space in the form of radiant energy, and in particular, of such great heat in the form of white light, is a consequence of the second law of thermodynamics, and must be a result if the second law of thermodynamics is supposed true, we must suppose that Nova Persei 1902 had all the necessary heat, but that, until that day, the second law of thermodynamics was, for some reason, not operative on it. Before the flare-up, then, the star in question was in a condition in which it showed little or none of the positive tendency. The tendency could hardly have been the neutral tendency, for, as we have seen, the neutral tendency does not form bodies at all, though there may possibly be such a thing as a body going through the neutral stage temporarily, when it is half positive and half negative. It follows, then, that the flaring up of the star must have consisted in its changing over from the negative to the positive tendency. And we may readily assume that similar circumstances give rise to other phenomena of temporary stars, and, since the temporary star seems to be the phenomenon that precedes the nebula, we may come to the conclusion that the pre-nebula condition of any stellar system is a stage in which that system follows the negative tendency, followed by a sudden change to the positive tendency accompanied by a great outburst of radiant energy. If we take 18 million as the approximate number of visible stars, and allow about 9 times as many that are dark or too faint to be seen, and take as an average speed of proper motion of the stars 10 miles per second, then, if we suppose that every star, on entering the Herschel drum, with the dimensions we have supposed, flares up as a result of the change from negative to positive, such flare UPS should happen, on the average, a little more frequently than once a year. This is indeed the average frequency of the appearance of temporary stars, and it is remarkable that most temporary stars appear to be near the surface of the Herschel drum. Accordingly, we may take this as the general explanation of temporary stars.